whatever reason, feel free to get a little closer to each other. But for now, what I want to do is get started by going over the practice test that we put up on Canvas. We've got a ton of other questions. In fact, I've got all of the questions that could possibly be on your test, actually, unless we create new ones in the next few days. So probably a good idea to pay attention, write things down. We are starting to record this. We're going to process it and put it up on Monday onto YouTube, and then we'll link you guys by email the YouTube channel so you guys can watch it again if you need to. Has everyone, let's show of hands, has everyone given this test a go? How many people have it? Okay. About half an hour. All right. If I take that screen up, can you guys see this one? Yeah. If you struggle too much, move over.
It's going to be, what are you doing? Alright, well, while Kate's screwing around, we'll get started. So it's going to be a very interactive session. I want you guys to ask a lot of questions. This is your one and only chance. You have to answer the questions. If you start asking me questions after this session by email, it's going to annoy me. So please either ask me tonight or Kate or Shrita tonight. And then obviously you're welcome to post on Canvas and use the office hours that we do provide, plus there's going to be another review session in class on Monday. But if you've got questions on anything, any material and what's going to come up on this test, please try to bring it up and ask me tonight, because I'm a very busy person. Okay, so let's go through this first practice test when we have this back up. Until then, I'll read it. Yeah, that should bring it up. Okay. All right, so if the date and time is 3 UTC on the 12th of June 2014, what time is it in Madison? So does anyone remember how many hours ahead Universal Coordinating Time is? Yeah. So yeah, during the summer it's 5 degrees. That's how tired I am. It's five hours behind in Madison. During the winter it's 6 hours because we have daylight savings time, right? So in the summer you're looking at a 5-hour difference between UTC, and in winter you're looking at a 6-hour difference. So what time then does that make it, and what is the only option that could actually possibly be correct? Right, it has to be on the 11th because 3 UTC, if you go 5 hours back, you're going to be getting into the 11th as opposed to the 12th. So that's the only option that could be correct. So yeah, that's the right answer. Okay, so pretty easy so far. The next one, again, it's just things you've got to remember more than anything else. Second question, what level is friction factor in the speed and the direction of the wind? So out of those ones, which is the fairly obvious choice again?
At the surface.
Right, at the surface. If you go above the surface, what two main forces are in large-scale motions are the important ones for meteorologists to understand airflow? If we're not at the surface, if we're above the surface. What two forces?
Pressure gradient force.
Pressure gradient force, and what's the other one? Coriolis force, right? What balance is that? Geostrophic balance, right? Is the air in geostrophic balance at the surface? No, because of friction, right? So at the surface, the friction upsets the balance. How does friction upset the balance? Can someone take a stab at how friction upsets the balance? What does friction do to the air? Right, increases the wind speed, and what force is dependent on the speed of the wind? Coriolis force, right. So the Coriolis force, the effect of the Coriolis is reduced by the reduction in the wind speed owing to friction. So therefore the flow gets thrown out of balance, and the pressure gradient force is the dominant force in that balance near the surface. So what does that mean about flow? What is it going to do as it goes across isobars? Is it going to go from high to low or low to high? High to low. It's going to start crossing toward low pressure, right? Because the pressure gradient force always points perpendicular to isobars from high pressure to low pressure, right? So as you might be able to tell, I'm kind of elaborating on problems in areas that I think are going to be useful for you. So notes is a good idea. Okay, this is kind of a stupid question because I've been teaching you about SKUTs, and I will make sure that the, yep.
So at elevation, when it's moving perpendicular or parallel to the isobars, is the high pressure on the right or left of the direction that it's going?
So the high pressure is going to be on the right of the direction it's flowing, because, well, that depends, I guess, which hemisphere you're in, because, well, at least in the northern hemisphere, the wind, or the pressure gradient force always points from high to low pressure, right? So the flow is going to be accelerated from high to low pressure. In the northern hemisphere, the Coriolis effect deflects the flow to the right of the motion. So as it's accelerated, it's going to be deflected to the right, okay? And so that you're going to have high pressure on the right and low pressure on the left, relative to the direction of motion. In the southern hemisphere, the opposite is true. The Coriolis effect deflects the flow to the left of motion, right? So just think about which way it's being deflected using the Coriolis force. So yeah, you scroll down a little bit on that. Yeah, maybe we need to zoom out, or maybe just hit the green thing up there. Yeah, a little bit. That's hard. Okay, so this particular diagram is a SKU diagram. As I said, what diagram does it look like that we're talking about today? SKU, right? So what can you guess about the name you think is the difference between a SKU diagram and a SKU diagram? Well, something's not skewed. Right, so the temperature lines are not skewed, right? Remember, temperature lines are called isotherms, right? Same therm, same temperature, right? So lines of constant temperature are isotherms. Pressure, isobars, right? You need to know those two definitions for sure. So this is again a vertical structure of the atmosphere, profile of temperature and moisture, or temperature and dew point. So this layer right here, we talked about these today, right? What is that layer called? Inversion, right? This is an inversion, because an inversion is defined as when the temperature increases with height or increases with altitude, right? So if the temperature is increasing, it's called an inversion, right? So that will be the right answer now. If we scroll over. Oh wow. Okay. I can go from where. Okay, so I think it says something about qualitatively estimate how humid it is at 400 millibars. Alright, so qualitatively, what does qualitative mean? Just give it a description. You don't really need to get numbers or any equation or anything like that. Just describe what you think about the situation. So at 400 hectopascals, the temperature is, well, at 400 hectopascals, the temperature is what, about -25 or something?
and the dew point temperature is about -52, -55. So qualitatively, how moist is the air at 400 hectopascals? Not very, right? Obviously not super saturated. In fact, in one of these diagrams, you're never going to see super saturation. It's just not going to happen. If the lines, in fact, come about this close together, right here, you're probably going through a layer that has some clouds in it, because you might not necessarily be going directly through the entire cloud, but if they get within a couple degrees of each other, the dew point and the temperature, you're probably in a layer that's nearly moist enough for clouds, so you might have gone through a broken layer of cumulus or something, or actually gone through the cloud itself. So if they get pretty close on the skew T, or the skew diagram in this case, then you might have a cloud layer, right? But in this case, way up at 400, the air is pretty damn dry, so clearly not saturated, and you wouldn't say high either, right? Because the dew point depression, the difference between the dew point and the temperature is pretty large. It's like 25, 30 degrees. So that's obviously low humidity, yeah, so that's good development. So which of these causes saturation as you, which of these, okay, this question is clearly worded really, unless I'm wrong already. All right, does anyone want to take a stab at reading that for me?
I don't, but I have a question about the other question. So like 30 to 25 is like pretty dry. What would we look at for moist? So
yeah, I mean, again, it's which is why, you know, it's no quantitative sort of it is moist, it isn't moist, right? It's a sort of a relative thing. But I would say moist, your relative humidity probably want to be 70% or so. I don't know if you want to add anything to that. This is kind of one of those sort of like just, you know, take a guess type of thing. But moist, you know, probably relative humidity 65, 70 and up. So if you look at a Kawsey's-Clapeyron curve, which is that curve in chapter 1 you used to diagnose the dew point and the temperature, if you take the vapor pressure of the dew point divided by the vapor pressure, saturation vapor pressure of the temperature, you get a measure of relative humidity, and if that number is less than 60, it's not moist. If it's over 70, it's definitely moist. So it's around that area. You're not going to get it wrong if, you know, it's kind of a take a stab at it more than anything else. All right, well, what are the causes of saturation when you see your breath on a cold day? All right, so does anyone want to take a stab at this question in the way that I said it, in other words, from the time there? No. This one I'll go to the board for, actually. So, you've seen this graph, and I've kind of pointed you guys in the right direction of it. And I think it should have been accentuated more in lecture, but this is what we call the Clausius-Clapeyron curve. On the bottom, we have temperature increasing along the x-axis to the right, and then saturation, vapor pressure. In the spotlight here. All right. First one you have before, I don't mind being in the spotlight. Okay. So as temperature increases, what do we know about the air being able to hold less or more water? Can the air hold more or less water when it's warmer? More, right? In fact, exponentially more, right? Which is one of the reasons why global warming, climate change, is such a big deal, because if we can hold more water vapor in the atmosphere, weather systems have more latent energy to work with, we have a big increase in the types of gases in the atmosphere that can actually then trap infrared radiation leaving the planet, and so it causes an accelerated process. And so as we increase the temperature, the amount of water vapor that can be held in the air actually increases exponentially, right? So this is called the Clausius-Clapeyron curve. So if I have a temperature of
negative 10 degrees Celsius right down here, right? And our body temperatures are up at about 40 degrees Celsius, right? Then the dew point of our breath is going to be pretty high, right? We're going to have a lot of moisture in there. It's not necessarily at saturation because obviously we're not breathing out clouds all the time, but it's somewhat close, right? So it might be here or something. So we might be pretty darn close to saturation. So let's take this point here and put it point A, right? Let's say we're this close to saturation. I might be exaggerating a little bit. But let's say if I just simply added a little bit of moisture to the air, because that's what it would mean if I went up here, right? It would be adding water vapor to the air if I went up from A. But if I go left from A, it would mean I'm cooling the air, right, to saturation. So it's one of those ways to reach this, which is saturation. This is easy. So if I increase the moisture, it gets to saturation, or I decrease the temperature, it gets to saturation. Let's take the air outside on a cold day, and let's make that point B. Right? So if I take point B, the air there, and point A, the air there, and I combine them, right? Watch what happens. I don't have to bend my line a little bit, but you get the point. If I take the two air masses, A and B, and I combine them, we actually find that we cross over the saturation curve and we reach saturation by mixing the air particles together, right? Because they have different properties, but if we mix them together, we find that we can actually reach that saturation curve, even though both of the air masses themselves are unsaturated. So mixing can actually generate saturation. Any questions? Nope. Okay. If you are in an area of low pressure, the weight of the air above you is what relative to average? Less than. We're actually talking today about Hurricane Michael in Weather Watch, even though I wasn't there, but I was listening to it over the live stream. And we were talking about how much mass of the atmosphere had been removed from the column inside of Hurricane Michael. So if we have 1,050 hectopascals on a regular day, and we're stood in the middle of Hurricane Michael, which has a central pressure at landfall of 919, what percentage of the atmosphere has been removed from Hurricane Michael? 10% of the atmosphere has literally physically been removed from that column, right? Which is incredible. So to do that, you have to literally put an extreme amount of energy and diverge the column such that you take away 10% of the atmosphere's mass, right? So it's an incredibly strong system if you think about it that way. That's the type of question that could possibly be asked on the test. If you decided to put something on, I could see you saying something like that. Okay, assume a constant density and normal warming of the air throughout the morning. What is the relative humidity at noon compared to sunrise? Anyone want to take a stab at this one? So just for some of these questions, right? Just think about it intuitively. Just think about just think about when you're outside, right? And you're walking around. Does it typically feel and look, depending on what time of year you are, I guess, does it typically feel or look drier in the morning or at noon? At noon, right? At noon. Good try. No, at noon, because, so think about it, sometimes you wake up and there's dew or moisture on the grass and the leaves and there's mist and stuff, right? But in the afternoon, it gets drier, right? Typically. It's a typical way to go. So what's happening there is the temperature in the morning is really low in comparison with noon, right? Because the sun is directly overhead versus just coming up. So the temperature increases very drastically through the morning. However, moisture, think about moisture. What are the processes that put moisture in or take moisture out of the air? What are the two important ones we keep talking about? Evaporation, condensation, right. So the only way to change the amount of moisture in the air, right, is to evaporate more water into the air or condense water out of it. So unless I have evaporation from a sea surface, right, or, you know, a puddle, which is clearly not enough to increase the atmospheric water vapor by enough to keep the relative humidity continuing to stay the same as the temperature rises, the dew point temperature, the amount of water in the atmosphere, is actually going to stay the same whilst the temperature increases. So look at this. Go back over here. You don't need to know what that is. Let's say we're here, right, in the morning, and when this goes to saturation, right, all we need to do is put a little bit more water in it and we'd have fog, right? But through the morning, we go this way, right? But we don't change the water in the air, right? We don't change the saturation vapor pressure of the water. So therefore, look now, we're much drier, right? The relative humidity is much lower here in comparison with here. That's because we've heated it up, but we haven't added any more moisture, okay? All right. Which of these is a limit on how accurate weather models can be? I don't know whether this type of question will actually be on the test, but yeah. But, so hopefully this one won't, because, like, I mean, I'm pretty sure I know the answer, but so clearly, let's go through step by step. So in terms of a weather model, right, it takes in measurements of the atmosphere, it takes in observations, right, to initialize the model. So we need the computer, which is going to run a program, right, that we wrote based on the atmospheric equations, needs some input, right? It needs to know where to start. So if we don't have enough observations, right, the model is just guessing what is going on in the region we don't have an observation, right? So for example, over the Pacific Ocean, especially before the advent of satellite data, there's a very sparse observation network, right? So we don't have many data points over there to give the model, and so therefore that is going to reduce the accuracy of the prediction that the model can actually do, right? So clearly, the limited number of observations is going to affect it. Observation areas obviously is going to affect it too. So we've arrived at the answer by just doing that, right? You see what I'm saying? Even though the terrain variability, there's questions, it depends on how the topography is handled in the model. But either way, getting to B with observation areas, if the observation is wrong, then of course what the model takes in to predict the future using the equations that we write are also wrong, right? The reason I stopped is because the equations are fairly good, right? Like the only area in which the equations are not good is in what we call closure schemes, which is basically where does the energy go when it dissipates? Because if you get smaller than the smallest box in the model, then what does it do with that energy? The energy in real life doesn't go away, right? But the model is at smaller scales than the model can actually resolve. So it's called a closure scheme. It's not something that I expected to know anything about, but it's why I was trying to think through whether that is a reasonable one. But yes, so this one will be all of the above. If you can identify 2 out of 4, obviously you can then jump to the answer very quickly, right? But I haven't seen many model questions, so I'm hoping there's not going to be too many, but I'll let you know if that changes. A can of soda is removed from the fridge and placed in a room with a temperature of 20 degrees. And the can temperature is 4 degrees. No condensation forms on the can. What could be the potential dew point? A, right? Only -10. Because if it was 5 and the can is 4, then the outside of the can would start to develop condensation, right? So there's only one answer that could possibly be correct there. The wind speed around an upper level ridge is what compared to the geostrophic wind?
faster.
Faster, right, exactly. So when you go from a trough, we talked about this quite a lot with the trough and ridges when we're looking at development of disturbances in the atmosphere, cyclones, right? Between the upper level ridge and the upper level trough, sorry, the other way around. Between the upper level trough and the upper level ridge, so when we say downstream, like I was making the point of today, downstream of the upper level trough and upstream of the upper level ridge, we're going to have upper level divergence, right? This is a result of the fact, or one of the results comes from the fact that around a trough, the winds move more slowly than they do around a ridge. And so around a trough, we call them sub-geostrophic, so under geostrophic, and around the ridge, we call them super-geostrophic. And this has to do with the pressure gradient, the excess pressure gradient force that exists at each. In terms of a trough, think about it. A trough is an area of what at its given height? An area of high or low pressure trough? Low pressure, right? So that wants to force air to go towards it, right? It's trying to accelerate the flow towards it. But the ridge is trying to accelerate the flow away from it, right? So we're pulling it back, and then we're springing it loose, right? Around the trough and then the ridge successfully. So therefore, around the ridge, it moves faster than the geostrophic wind because the pressure gradient force reacts too quickly. The acceleration is too quick for the Coriolis force to adjust to. And you're not in geostrophic balance. You actually exceed geostrophic balance around a ridge. The dew point depression, which again is the difference between the temperature and the dew point, is 30 degrees with an air temperature of 10. Qualitatively, what is the relative humidity? So again, that comes down to another question that was asked up front here, and that is meaning that it's going to be low, right? It's not zero. There's some moisture in the air pretty much everywhere at all times, but it's pretty low, 30 degrees dew point depression, right? So when would a particle move vertically at the moist adiabatic lapse rate? This one should be pretty easy for you guys, given the fact that we talked about it a lot in the last couple of weeks here. So it's going to be going at the moist adiabatic lapse rate if it is saturated and being lifted. Why would it not be D? Why would it not be saturated and be brought down? What is wrong with that statement? Because you might think, oh, it's saturated, it's going to fall in the moist if you throw it up or down. But why can't that statement be correct? I've explained this to a good few people already. I don't know if you guys remember. What's wrong with that statement? What happens when air is forced to sink to its temperature? If it rises, what happens? It cools. Why does it cool? This is expanding using energy to do so, which lowers the kinetic energy of the molecules in the particle, lowering the temperature. But if it gets forced to sink, what is happening then? The pressure is not going down, obviously, anymore. It's going up, right? So the pressure goes up. It forces compression on the particle, right? So if we compress the particle, we actually, the system is getting done work on by its environment, and it's squeezing it. That's increasing the kinetic energy of the molecules, and that increases the temperature. So if we force air to sink, then the temperature is going to increase. But what process there is going to increase the moisture? Again, we need evaporation or condensation. And the only way we're going to get continued condensation is if we cool it, and it continues to be supersaturated, right? And then we get condensation. But if we warm it, there's no addition of moisture there, so we're going to get dry straight away. As soon as you force that to sink, it's going to get dry. So that air particle is going to be dry in descent. It cannot be saturated and being pushed down. It just can't happen. So that statement is completely incorrect. Does that make sense? The Coriolis force is what at the equator? Zero. Exactly. I'm going to clarify that one. Gravity and vertical pressure gradient can form this type of balance. We talked about this on my first lecture that I gave to you guys. What is the balance in the vertical? What two forces are involved? Alright, just it's up there. Well, what's the balance called? Hydrostatic, yeah. Yeah, so that was fairly easy. It's called a static stability, right? We talk about inertial stability, if there's like a geostrophic balance. If there's a hydrostatic balance, then it's a static stability, not a dynamic or inertial stability. The above station model, what is the temperature of it? 14 degrees. So that top one is the temperature in Fahrenheit. The bottom one is the dew point temperature in Fahrenheit. And the pressure over there is going to be 998.1. This will be easier for those of you who have actually taken the discussion section because we did this. But for those of you who didn't, those last 3 digits are actually 1 decimal and then 2 integer values. And so that would be 998.1. And the reason I know that is because the other options are 1098.1. There's never been a surface pressure that's ever been that high. So I know that that can't happen. And then if it was 898.1, again, we'd be inside the middle of a hurricane that was 25 millibars stronger than Hurricane Michael. So I'm guessing with that wind, we're probably not. So that's how you can deduce that information from there. Which direction is the wind coming from? North, right? So we did the photographs earlier. Remember I showed you photographs? And I said, if it's pointed toward the 0 at the bottom, then that's northerly, right? So this wind right here is a northerly wind, which means it's coming from the north, right? What's the meteorography? Well, I've already just told you that, 998.1. What does, okay, this is a pretty exact question, but what does red represent? We just talked about this today. Very, very quickly at the end, recap it a little bit on next Friday, which I'm hoping to take the lecture again. What does red represent on the radial velocity radar image? Yeah, so I have to think about this for a second. Obviously it's not hail or excessive heat because we're talking about the directional movement of the flow. Red is it a word? Okay. I'm going to double check that for you guys. I don't, I do this stuff and I guess, yeah, it would probably be away from the radar. Yeah, it's going to be away from the radar. We'll double check, but I think it's away from the radar. So when you look at a radial velocity image, what you're looking at, right, I was going to talk about it, but we're here now, so I may as well. If I have, this is my version of an ambulance, if we're stood here, relative to an ambulance moving this way, right, every pulse is further apart, right? Every sound wave that's emitted is further apart, whereas over here, every sound wave is getting closer together. So the sound appears differently. If we emit electromagnetic radiation using a radar in quick succession, then we're able to measure with the difference between the 2 pulses, how long it takes to get back, how far the object that we are measuring with the echoes has moved in that time, right? And so that's the dual Doppler radar, that's how we do it. And so when we send out pulses in a storm, we can see in the storm whether how fast and in what direction in 2 dimensions the flow is moving. And as I told you earlier, we infer reds and greens, which means that they're going opposite directions very close to one another as air rotating, right? We can't see 3 dimensions with the radars, but we know that if it's going really close together, different directions, that means the wind is probably going in circles, right? So that's how we infer rotation in storms. Which of the following is not a factor in the production of rain? The updrafts in the cloud, relative size of droplets, number of ice crystals in the cloud thickness, and the electric charge of droplets. What do people think? Yeah, the electric charge of the droplets. Because the updrafts in the clouds, the rate at which they, or the speed at which they are, determines how high the supersaturation can get, because how long it takes the precipitation processes to occur. And it can also suspend larger droplets. The size of the droplets obviously matters. The number of the ice crystals, which we know initiates the Bergeron process, and that rapidly leads to nucleation of the cloud droplets, or priming of the cloud droplets onto the ice crystal, and that's how you generate precipitation. And then the thickness of the cloud also is going to matter to collision and coalescence process. The more there is in an area, the more cloud droplets there are in an area, the easier it is to collide and coalesce, right? Which state of below best describes the curvature effect? Large droplets fall faster than small droplets evaporate more quickly than large droplets, small droplets collide and coalesce more easily than large droplets. It explains the 6 out of 7 directions. Well, obviously, the last one's stupid. The large droplets falling faster than small droplets has really nothing to do with the curvature effect. And large droplets collide and coalesce more easily because they're larger. So you could do it by a process of elimination, but small droplets do evaporate more quickly than large droplets. If you think about it, the surface area to volume ratio of these two, this one's got a much, much bigger surface area to volume ratio, right? Because this one, there's a huge amount of volume in comparison to the edge of it, in comparison to this one, and so molecules can easily evaporate, right? They can easily escape the surface of the droplet, and so because the droplets are curved, right, it makes it very easy for water molecules to actually escape the surface of the droplet. And so that's what the curvature effect limits the ability for droplets to grow. Okay, that's why we need nuclei, the soluble and insoluble cloud condensation nuclei that allow precipitation processes to occur. Right? An inversion represents an extremely stable layer of air because that rises into the inversion will eventually become what than the surrounding layer. This should be, again, pretty easy for you, given what we just talked about. So, if the parcel is rising, what rates is it cooling at? Either the moist or the dry, right? So 6 or 10 degrees per kilometer is cooling at. What's an inversion? Warms with height. So we know that a parcel rate, trying to go through that level, is eventually going to become colder pretty darn quickly than an atmosphere that's actually increasing the temperature with height. So it's very, very stable, right? Because it prevents the air parcels from rising through it. So it's going to obviously become colder and then, as a result, more dense than the air around it, right? The conditionally unstable atmosphere is what with respect to unsaturated and what with respect to saturated. This is obviously really easy. So, well, it's only easy given that we've talked about it a lot, and I'm hoping that it's easy for you guys now. So, what is the answer to this question? Right, C, right? So it's stable with respect to unsaturated air, but unstable with respect to saturated air. That's that condition I keep talking about. Condition on it reaching saturation. Why might you expect there to be a height but no temperature dew point or wind in Elko, Nevada on the 850 millibar map? I don't know who wrote this one, but yeah, so up at those elevations, the 850 hectopascal surface is actually under the ground, right? So, which is why if you look at it, if you look at our website, if you look at Pivotal Weather or any one of those websites and you plot 850 temperatures, does anyone know why we use 850 hectopascals to plot temperature in the atmosphere? Has this been explained to you at any point?
Isn't it just above where the sun warms and cools?
Exactly, right, yeah. So if we're here at the surface and it's daytime, we're going to get radiation that's going to heat and mix the air by causing it to rise because it becomes unstable, right, and turns over. This layer of air is going to warm each day and cool each night, right, like we used to. This is called the boundary layer. The boundary layer warms and it cools each night. But most places on the planet, the boundary layer ends just below 850. So 850 hectopascals is literally just around the top of the boundary layer. What that means
is that day to night, the temperature at 850 doesn't change. So that means we can track movement of warm air and movement of cold air, right? So if we have a warm air advection, we can see it, and it doesn't change colors every single time we move 12-hour periods, right? Because that would be like an epileptic fit or something. So we want to remove that change on a diurnal basis. So we get rid of that by plotting the temperatures at 850, and we can see regions of air moving around. But over the Rockies, right in the west, you'll see it change day to night because the surface is around about 850 or maybe even higher, some places at 700 hectopascal. So when you look at 850, what you'll notice from day to night is you'll see it go warm, cold, warm, cold, warm, cold, warm, cold in the west, and that's because the surface is actually on the ground or below the ground. Does that make sense? It's the same reason we use sea level pressure, right? Because if we try to track pressure systems based on surface pressure, we completely lose them as you go over the Rockies. If the flow goes over the Rockies, we would lose the low pressure, right? Because the pressure is so low. What do you think, there's a 700 millibar hurricane or something going over the Rockies? No, the surface pressure is 700 millibars. But we need to interpolate that to the sea level pressure so that we can actually understand where the movement of pressure systems is over the topography. So that's why we do the same with 850, but it does have some issues over high terrain. Okay. The surface low pressure, that moves from just something of Madison. I don't know whether this is like a mistake or what, probably is a mistake. To a position just east of Madison would most likely produce geostrophic winds that shift from what to what. So, I think a couple of people asked about this question. It looks like you can't answer it at first, but you actually can, because if it moves from some position to a position just east of Madison, just east of Madison.
Look, it's south of Madison. I forgot.
What?
I mean, it was meant to be south of Madison.
Okay, is that what it was meant to be?
Yeah.
Okay, well, now we move, even if we didn't know what it was, right? Now we know that Madison is here, and it's moved to here. So if I draw isobars around this, right? It's just east, well, the point of the question is saying it's just east of Madison, and the isobars are going to go around the low pressure, right? Because they're rings about the lowest central pressure, and it's getting greater pressures to go out. So it says geostrophic winds for a reason, because it wants you to think about the pure balance between pressure gradient, which is going to be pointing this way, right? And the Coriolis force, which is opposing it. That's geostrophic flow, right? So what is the direction of the geostrophic flow at Madison? Northerly, right? It's coming from the north. So V denoting a wind. The direction of the flow is to the south or a northerly wind, right? What if we had friction? It's not going to be a geostrophic balance, right? If we add friction to the wind, then the flow is deflected across the isobars toward the low. So if it said what you think the wind direction will be in Madison, it didn't say geostrophic, you would say northwesterly, right? Because of the deflection owing to friction, okay? But if it says geostrophic, you're ignoring friction because friction is not included in the geostrophic balance. Okay, so this next one right here is an 850 millibar map, and it says which state is experiencing cold air advection. You can do this up at 850, right? So what do we have to have about the wind relative to the temperature lines to have cold air advection? Wind has to be moving from what to what in terms of temperature? Cold air advection. Wind has to be moving from cold to warm, right? That means the cold air is literally being advected by the wind. Move from one place to another is all that advection means, right? So the only place that that's happening, this is the -10 isotherm, is in Michigan.
right? The winds are coming from the north, going to the south, and there's cold air to the north and warmer air to the south. That's cold air advection. Over the east coast, the winds, because we know that they rotate anti-clockwise or cyclonically around flows, right? We just look at the pressure analysis or the force balance analysis I just did to realize that. But the flow is going southwest to northeast over here, right? Following these isobars. And if that's true, the air is warmer here than it is here, right? So over the east coast, we have warm air advection. And we also have warm air advection in Minnesota, right? Because the winds are coming from the northwest. It goes -5 and then warmer from Minnesota. So we have warm air advection in Minnesota too. We barely have any advection across the Midwest. And the only place we really do have cold air advection is in Michigan, right? And what is the approximate wind direction at 850 at Madison? So it's pretty much the same as the last one, right? It's coming from the north. Does that make sense? All right, 27. The city that we can expect to see the strongest surface winds. How do we measure? Like, what is causing? Yeah. It's north. Wait, hang on. What is the approximate wind direction at 850? Yeah, it's northerly, so south. It's pointed south. Yes, exactly. Okay, so refer to this map. The city you can expect to see the strongest winds is what? So, what is the only force that drives horizontal winds? Pressure gradient, right? That's the only force that drives the winds. Remember, the Coriolis force deflects the winds, doesn't accelerate the flow. And in fact, pressure gradient force, or what we call buoyancy force that we were talking about earlier with Kate, is actually imbalance between the pressure gradient pointing up and the gravity pointing down, because the air is warmer and less dense, and so there's an excess pressure gradient force pushing it up. So actually, pressure gradient is really the main driver of any flow, up, down, sideways, or whatever. So if the pressure gradient is larger, the wind is likely to be larger in that region too, right? So wherever you see on a map, if you have closely packed or a large gradient in isobars, then you are going to have strong winds. So most of this map barely has any wind, right? In fact, I think the next question asks at Fargo what's going on, or where is, it might say where is the weakest winds. Yeah, so the weakest winds are at Fargo, right? Under a big dome, high pressure, the wind is very, very calm. There's not a large gradient in pressure, so there's going to be no acceleration of the winds. It's going to be very, very weak winds. So the closest packed isobars are over Michigan again, right? They're over Detroit, because the 992 and 996 hectopascal isobars are really, really close together. Does that make sense? Any questions on that? Okay. So that's your answer 27, 28. Which of these are not generally heated by the sun? What's the answer to this one? Air. Yeah. It might be a trick question at first, but the way we feel heat, I did explain this on one day that I lectured, the way we feel heat is by thermal infrared radiation, right? And it needs to, the sun's energy, which is visible and UV part of the spectrum, needs to be absorbed by something that the radiation can actually be absorbed by. So the Earth's surface absorbs visible radiation, right? And then it re-emits it as infrared radiation, because infrared radiation has a lower frequency. We do the electromagnetic spectrum up here, and on this side we have gamma rays, right? And over here we have radio waves. Somewhere in the middle we have the visible part of the spectrum. We know that the sun emits in the visible part of the spectrum. Why? Because we can see it, right? If we were walking around blind, then no, the sun might have been emitting in a different part of the spectrum, and we would actually adapt our eyes, and we may have infrared vision, right? It's pretty cool to think about. But the Earth emits in the infrared part of the spectrum because it's cooler, right? So it has less energy. The Earth has less energy, the sun's kind of obvious, but its emission has lower energy. So its frequency is lower, it emits in the infrared. So the sun's energy spectrum is something like this, the Earth's is like this, it barely overlap at the edge of the visible and the infrared. So on a hot day, right, if the sun is the same angle as the next day when it's a lot colder, for example, just the other day, right, we had a big cold front come through, temperature dropped 30 degrees in like 4 hours, right? If it's sunny on those 2 days, why does our face feel hotter on the day when it was warmer? The sun's at the same angle, it's the same strength, but we're having more trouble losing infrared radiation from our skin because the gradient in temperature is not as great when it's warm as when it's cold. So we feel the heat buildup. So when you're thinking about the sun's rays and radiation, the sun actually is, the atmosphere, sorry, is transparent to the sun's radiation, but the atmosphere is not transparent to the backscatter or the back emitted radiation of the planet, which is the thermal infrared radiation, right? So that's the radiation that actually gets emitted back. So, long-winded answer to that one, the sun does not directly heat the air, it heats everything else on the surface of the planet, right? Energy cannot be transferred into or out of the atmosphere by what? Cannot be transferred into or out of the atmosphere by convection from the surface, radiation from the sun, radiation from the surface, flux of the radiation from the surface. And none of the above. So that's kind of a double negative, I guess, but the answer to that one I think should be none of the above, because as I've just said, well, okay, so this, the thing that it's getting at here is there are certain elements or molecules in the atmosphere that can absorb radiation directly from the sun. What is one obvious molecule that can absorb the sun's radiation? Cryptically give you a clue, why is there a tropopause? Why did we saw the thunderstorms earlier, right? And they were hitting the tropopause, and they were causing those overshooting tops, right? Why is that even there? Why don't they just keep going until space?
Ozone.
Ozone, right? Ozone is a molecule that absorbs the UV radiation, or in parts of the UV radiation from the sun, right? And so what that's doing is heating the air up around it in the stratosphere, which is why the tropopause exists. The tropopause is a layer of stable air. It's a layer of warmer air as we go up into the stratosphere, because the ozone up at that height, where we had enough energy from the sun to dissociate, I made up a new word, dissociate oxygen molecules. There's enough energy up there to do so, and we end up getting oxygen radicals, which then react with oxygen itself, the diatomic molecule, we get O3, right? And so that oxygen layer, the ozone layer up there, is absorbing radiation from the sun. And so there is an input of energy from the sun. It's just not in the troposphere that we actually, most of it's transparent on the way down. And obviously, you know, we know that we get heat from the ground, and that's why we feel the warmth of the sun. So one other thing to point out is if I draw a skew T diagram, and I draw this type of structure during the day, right? So this would be temperature going across the x-axis, and this is height, right, increasing there. Why would I draw it like this at night? Say this is the day, and this is night. What has happened between the day and the night to the temperature? It's decreased, right? That's because the surface is emitting infrared radiation, but there's no radiation now coming in from the sun, right? So we're actually losing heat from the surface to the air. So the surface actually becomes colder at night than the air above it, which is why thunderstorms tend to die out at night, because they were unstable, right? But at night, they become stable near the surface because there's no input of energy from the sun to keep it warm and buoyant and unstable. We now have this really stable layer near the surface. It's called a radiational inversion, if you wanted to know. All right, in a hydrostatically balanced atmosphere, surface pressure is a measure of what? The weight of the air above us, right? So hydrostatically balanced means that the two forces, gravity and pressure gradient force, are completely balanced, and therefore there is no divergence and acceleration, all this other crap. It is simply the weight of the column above it. Does that make sense? Okay, cool. Someone said yes. Latent heat is the amount of energy stored by water vapor. It's released when water or vapor in a parcel condenses. Power, strong thunderstorms, are all of the above. All of the above, yeah, good. Because it is the energy stored in water vapor, because it powers tropical cyclones, right? We get really high really high moisture from the surface, and we flux it up through the atmosphere. When the vapor condenses in the liquid, we release the heat of the gaseous molecule, and it has latent heat, and that powers strong thunderstorms as well. And so, obviously, the answer, therefore, is all of the above. So we look for the jet stream on which pressure surface, and I'll follow that question up with why. So which is the answer first? 300 millibars, 300 hectopascal. So relative to the depth of the troposphere, where is that? Near the top, right? Very close to the tropopause. So it's actually in the middle latitudes, which is the latitudes that we live in. That's just beneath the tropopause most times a year. In the tropics, tropopause is higher, probably more like 200 or maybe 100 hectopascals for the tropics, right? But in the extratropics, that's a pretty good estimate of where the top of the troposphere exists. So why may we be interested to look at the jet stream? And when we say the jet stream, we're looking at troughs and the ridges in the jets, right? Why do we care about those types of structures or disturbances at that level? And what does that tell us about what might be going on underneath? Someone take a stab. So what's going on between a trough and a ridge that I talked about earlier? Divergence, yeah. So why do I care about divergence at the top of the atmosphere? What does that mean it must be via the law of mass conservation, mass continuity, right? If I take air away from one point, right, and I have a layer or a lid, right, it's a fluid boundary, it's not a physical material boundary, but the tropopause is effectively a lid on the atmosphere, right? So if I take air away from a point at that height, what necessarily must have to happen underneath that? Air is going to rise up, right? And why do we care about air rising? What is the importance for understanding the development of weather systems, especially in the middle latitudes, for air rising? What does that do underneath, or at the ground, underneath the air rising? Yeah, we lower the surface pressure. As soon as we start lowering the surface pressure, air starts to converge towards it and it gets turned, and then we get cyclones, right? And anticyclones, if the air is converging at upper levels. So we care about the jet stream and the pattern up there because we get to forecast based on some of the diagnostics and the prognostic variables that we developed in meteorology to understand where surface pressure is going to change. That means we know where weather systems are going to develop. That's how we know where frontal systems are going to develop and how precipitation and thunderstorms and things are going to evolve in several days in the future by looking at the 300 millibar surface and seeing the disturbances in it. Which is the largest diameter? This one should be very easy. Raindrop, right? Drop down, yeah. Precipitation in clouds over Madison is not formed by rain droplets growing at the expense of cloud droplets, evaporating, ice crystals growing by the Bergeron process, melting snow, cloud droplets forming first rain through random collisions with each other. So I guess you just pick which one is it typically formed by? B, ice crystals, right? We very rarely get warm rain processes. It's called a warm rain process when you just get collision and coalescence. Where did Professor Trippery say there was one place where you can get a lot of warm rain?
Wasn't it like Miami?
Yeah, like in the tropics, you can get warm rain processes because there's so much water vapor in the air, right? But up here, typically we need ice crystals to get that process going. Then, I'll go back to my curve here, it's getting a little messy. Take this off. Okay, so if this is the saturation vapor pressure with respect to water, right? And I'm going to draw now the saturation vapor pressure with respect to ice. And I'll draw it underneath this line here. This has to be 0 degrees, right, where ice can start to form. So if this is the saturation vapor pressure with respect to ice, and this is the saturation vapor pressure with respect to liquid water, and I am at saturation at -10, or let's say I'm -20 because that's typically where these processes start. And the relative humidity with respect to liquid water is 100%. What does that mean the relative humidity is with respect to ice? Much higher than 100, right? So that means that if I have loads of cloud droplets and I have little rain droplets starting to form, and it's about 100%, but because of the curvature effect, these guys are going to find it very difficult to begin to grow, right? But if I put one ice crystal in there, the vapor pressure that that thing feels is huge. So all of these will deposit on the ice immediately, and it'll explode, right? And that will shatter out loads of other ice crystals, and the same thing will happen through the cloud. And that gets the process of precipitation development going very, very quickly in comparison to the warm rain process, right? So that's the typical one. So then the answer to that one would be C, C, random collision would not happen because it would lead to the curvature effect and end up evaporating. So what type of cloud are we seeing here? You guys should be very good at this by now. Looking over at Kate. C, yeah, we're looking at I think it is a pretty difficult question actually. What do you think? Cloud expert?
But that's not an answer.
Yeah, so yeah, it does look like cumulus on the horizon, like a cumulus congestus, right? It's not a cumulonimbus, but because it's puffy on the top, then whenever you see the puffy type structures to the cloud, it means that the air is formed that cloud by being unstable, and that's a cumuliform type of cloud. Nimbostratus obviously is like stratus, but thicker, producing rain, right? So I've already talked to you about some of this. I think Kate's mentioned to me a few times. A lot of you have posted pictures of cumulus congestus and said that they were cumulonimbus. The one thing that you have to see if it's cumulonimbus is rain, right? Because rain, the nimbo part of the cumulonimbus, is stating that it's rain-bearing. That's what it physically means. And so if the cloud you're looking at is a really tall and puffy, but there's no sort of rain or anything coming out of the bottom of it, then it's probably a cumulus congestus. So I think Kate was saying very few have actually got that so far. So that might be a difficult one to get now, now that it's getting cold and stable, right? But good luck. When we want to expect rain to start to fall from a warm rain process, so obviously we just said this, Miami, Florida is a good place where there's a lot of water vapor in the air. Which of these do not occur in the greenhouse effect? Absorption of infrared radiation by atmospheric gases, re-emission of infrared energy by atmospheric gases, absorption of solar radiation by carbon dioxide, emission of infrared radiation by the ground. The absorption by carbon dioxide, right? We just talked about the fact there's very few molecules in the atmosphere that absorb directly from the sun, one of those being ozone. Otherwise, CO2 absorbs in this part of the spectrum. This is the whole point, right? It absorbs in this part of the column. Now, one other side tidbit here for you guys. Water vapor is actually a stronger greenhouse gas than CO2. But why do we care less about the addition of water vapor into the atmosphere as we warm than the addition of CO2? Can anyone potentially give me a reason why that might be? So, just for you, the atmosphere, right, has a lot of water vapor in it, and it has a lot of CO2 in it, okay? They're both greenhouse gases. They both absorb in the infrared part of the spectrum and re-emit in all directions, and thus reducing the amount of energy leaving the Earth's atmosphere. But as we warm, we're going to put more H2O into the air, right, because the air can hold more water vapor. Why do we care less about that process than we do about the addition of CO2, which actually has a lot lower concentration in water vapor? Yeah.
Because CO2, we see it as like man-made, that we're doing it when...
So that's true, but it's not the right physical answer. Does anyone else have another stat? Why do we care about CO2 more than water vapor?
It's longer lasting.
You're right, it's transient. H2O is very, very transient mobile. I'll give you the answer. Basically, there is what we call, let's say this is the infrared part of the spectrum, and this is what's leaving the planet, right? H2O is, let's say it absorbs in this part and this part. It absorbs in a few different areas. But let's say it absorbs all of it already, right? So everything leaving the planet in this part of the spectrum is already being absorbed. So if we keep putting more in, it doesn't matter, because there isn't any more to absorb. It's all being extinguished or absorbed before it leaves. So we can't make the effect any worse than it already is, right? But CO2 is in a part of the spectrum where it only absorbs a little bit of it, right? We have nothing else in that area. That's called an atmospheric window, right? And in that part of the spectrum, if we keep piling on CO2, with one of the only windows that there is, then it's going to shut down more and more and more of the infrared radiation that's going to leave the surface of the planet, right? So we really care about that one because it's in such a prominent position in the spectrum, and it can absorb from where nothing else does, right? So that's why we care about it. So we can do all that. What does a large amount of CAPE indicate? Large amounts of the non-acronym version of that word, yeah. So yes, it's obviously B, it's just asking if you know what it stands for. What does latent heat release do that can help develop a tropical cyclone? I mean, that's, I don't know if we actually talked about this, but don't have an idea. No, so latent heat release doesn't reduce energy, it provides energy, right? But what does latent heat release do? What is heating the air probably going to do to the pressure? Reduces the pressure, right? If we heat the air, it's becoming less dense, we're lowering the pressure. So that's why we care about latent heat release that way. True or false, and then I'm going to take some questions. I want you guys to think about anything you want to ask me after this. True or false, upper tropospheric divergence is associated with falling surface pressure. Is that true or false? True, we just literally talked about this with the 300 hectopascal surface, right? If you have divergence up there, then we're going to have falling surface pressure because the air is going to rise and diverge, and low pressure is going to form underneath. Seeing something before you hear it is an example of the Doppler shift. Well, I don't think it's a Doppler shift. I think that's like if I were to bang something and then run away really quickly and bang it again and let you, like, I don't know, I'm making shit up. So let's forget about that one. If it comes up on the test, I'll give you points back for it. All right, ice crystals can form in clouds easily at negative 20 degrees Celsius. True, so that's the level that the cloud top really wants to get to generate ice crystals, right? Relative humidity of 4,100% is common under normal conditions. Well, I'm going to let you decide that one for yourself. A minimum sea level pressure of 1,000 millibars is common under normal conditions. That's pretty common, right? A surface area of low pressure with sea level pressure of 972 is considered strong. This is actually a bit of a stupid question. I wouldn't put this one on the test. Can anyone think why I may think this is a stupid question? Now think about how do we as human beings measure how strong something is? Like, you know, for example, a tropical cyclone or a tornado, or when we're just walking around on the street. If it's calm versus it's blowing a gale, we're going to be more noticing the gale, right? So what are we judging the weather by there? We're judging it by what variable? What variable are we judging the strength of the weather phenomena by in all of those examples?
Wind speed.
Wind speed, the speed of the winds, right? We don't care about the pressure, not necessarily, right? It's a pretty good measure of tropical cyclone strength because all of the cyclones are in the tropics. So all the ambient pressure in the tropics is pretty much the same. However, at the poles, the pressure is much lower than in the tropics, okay? So, at the surface. So, why would I say that this question, saying that a 972 millibar low is considered strong, is not a very good question? What does it depend on? It depends on where you are. That's a very good point. Why does it depend on where we are? What is the strength of the winds going to be if I put a 972 low in the middle of this? Let's say this is the North Pole, and then this is the equator, and the surface pressure of the equator, on average, let's say it's 1,030 hectopascals. And let's say up here it's 980 hectopascals. If I put a 972 low in here, oh, that's a 4. Good try. Okay, put a 972 low there, right? And 972 low here. How many contours am I going to draw here versus here? A lot more here, right? There's going to be a ton. And they're going to have to be pretty closely packed because all the pressure around it is forcing the flow in. Up here, we only have 2. Right? So the winds, where are the winds going to be stronger? The one in the tropics, right? Because the ambient pressure in the environment is much higher. So what therefore am I saying? It depends on more than the actual physical central pressure. The what of pressure? The gradient in pressure, right? The gradient between the environment and the center of the low matters way more than the actual central pressure, right? So a 972 low up in Iceland, we get these all the time in Britain. The 972 low, you'd have some breeze and there'd be some showers and blah blah. If you had a 972 low come through Madison, you'd know about it, right? Because the pressure over the central United States is much, much higher ambiently than it is over the seas near Iceland, okay? So that is just something to bear in mind. I don't know how I grade that, but I wouldn't put it on the decimal anyway. So, wind bobs point in the direction the wind is going. False, right? Wind bobs point in the direction they're going. That's a weird question too, right? I mean, like, I always think about it as if I fired an arrow into something and then it's going that way and the quiver is the bob. So, in that sense, I would say that's true, but again, it's kind of a stupid question, so, okay. Skip it again. The temperature could be much higher than the dew point at the surface under normal conditions. That's true, yeah, it could be much higher than the dew point. The Phoenix, right, if you think about it, it's going to be really dry. Half of the air is composed of carbon dioxide? That's completely ludicrous. In the middle latitudes, air flows directly from low pressure to high pressure. That's obviously false. Even if it was high pressure, low pressure, which would be, it's still false, right? Why is it false? Why would it not flow from high to low? Coriolis effect. Okay, cool. Any questions on that? I'm going to take just general questions. I want you to think long and hard about anything that you want to ask in the next half an hour or so here. I'll take. Yep.
Is the test curved?
It is most likely going to be curved, I would think. Yeah. Was that what everybody can believe that?
Can I say something?
Yeah.
So the class itself will be curved at the end with respect to the homeworks and the tests together. The test itself won't be curved.
Right. Yeah. So the class is going to be curved. So there is probably going to be a large disparity in grades. It's fairly obvious. And so we are probably going to do a general curve. Yeah, that's right. Yeah. So there will be a curve, but there might not be a curve specifically on this individual test. But everything will get shifted at the end of the class. All right. Yep.
What's like the format?
So it's going to be very much like this, right? So it's going to be like take 10 true or false questions at the end, and then the rest of them are going to be similar to this. So you see how they're quite similar to like the test your understanding questions. So those are good practices from chapters 1 through 4, 6, 7, 8. What else do we do? That's it? Okay. So those chapters, if you can do the test your understanding, and you go to my email real quick, or the downloads that I actually have like all of the, as I said, all the tests here. So we were thinking of putting some additional questions on Canvas. So it looks like there's a few notes going on. So I can do that as well. Again, they're very, very similar format to what we just went through. Additionally, if there is no questions and you guys still want to hear more from me, which I'm happy to talk, then I can go over more of these questions. But very similar format. So I would say that if there's going to be 50 questions, then I would just breeze through the true and false in like a couple minutes. They shouldn't be very difficult. They'll be very easy, like the ones we just went through. And then budget your time for the last, like, I think it would be 40 questions. So it's going to be like 1 a minute, right? Or maybe a little more than 1 a minute. Sorry, not more than 1 a minute. 1 per like 70, 80 seconds maybe. But you're going to have to budget your time from that. So that's the way I would approach it. Just breeze through those and then budget your time per question. Yeah. I don't know. I'm not sure. No. Yeah, it's going to be just weighted based on like it's 20%. Is it 20%? Is that it?
Each exam is 15 up until the final.
Is it? Okay. All right. So whatever it is, it'll be like of the total number of points available in the class, it'll be like that percentage of it. So I don't know how to answer that. Yeah.
Is the testing class on Wednesday?
Yeah, so the test, how's that going to be done actually?
I think he's just doing it in here.
Yeah, but you can obviously tell we don't get a huge amount of communication. I actually told everybody in my discussion section that he was in China this week. Turns out he's not in China at all, he's in Colorado. So much to my amazement when I got an email back from him. So I am the next door to his office and I get probably less communication than you guys, so I'm doing my best to communicate what I believe is going to happen. But from what I understand, yes, they will be. What is actually, I think, going to happen though, because obviously everyone, it should actually be pretty full in here on the test day, I hope, if they've got the message of people that aren't coming. Obviously everyone's sitting really close to one another, so I wouldn't, well, A, don't copy anyway, because you'll get thrown out of the university, but 2, definitely don't copy if you're trying to get results, because all of the exams are actually going to be different. Not different like overall, but all the questions are going to be jumbled, and they're going to get different colored exams depending on where you're sitting. So just I shouldn't be telling you secrets behind cheating, but definitely do not cheat. It's obviously against the rules. So, but everybody's going to receive a different colored booklet. There's going to be 50 questions just like this, and then I think 10 true or false. Yeah, it's just multiple choice. So there's no written answers, no quantitative answers. It'll be grading, Paul Schreeder for adaptive grading, 400. Yeah, we can give him a round of applause while they're cheering. So any more science-based questions? Right? Yeah.
How do you recommend like you study?
I think I've done this question about 100 times, and that's not actually an exaggeration. As I said to most people, obviously this is an important place to come and ask questions and listen to kind of the understanding behind the questions. I would go through, I'll make sure we get some more practice problems up. So as I said, I have about 4 or 5 previous tests, so I'll throw another one up on Canvas. Go through the questions, but do what I did kind of in your own head as you study, right? If you understand or you get the right answer in a question, make sure you actually understand the concept behind it. That if you change numbers, you change the position of low pressure systems, if you change things around, make sure you're actually able to understand the concept. So go back to the chapter in the book, read that part of the book, and make sure you understand the part about it. I would also use Canvas. I've got a midterm discussion thread up there. So if you have any last minute questions, throw them in there, and you can also discuss with people. Again, like I said earlier, I would get it together in like a group of a few people and just discuss answers together, go through a practice. There's the practice problems that we'll throw up, and then maybe to test your understanding problems of the chapters. So again, the level of the questions is very similar to the test your understanding problems in there. So that's a good place to go to study. Any more science-based questions or? No. Yeah.
Is that also like
yeah, so if the cloud top is above -20, ice crystals can form, and so the precipitation type is dependent on how warm the atmosphere is beneath the cloud, right? If the atmosphere stays below 0 to the surface, it's going to fall as snow. If it gets above 0, it's going to fall as rain. So precipitation by ice crystal processes needs to be above -20. It can still fall as rain, yeah. Yeah.
You said that the Oreo is the model of high pressure to low pressure.
Because as the air flows from high pressure to low pressure, it's going to be deflected right to the right of the motion by the Coriolis. So it can't flow from high to low over large distances, right? Other questions? I like that. Yeah, I just I'll go with that. Thank you, sir.
It's like the relationship between nuclei concept and then the insoluble aerosols.
Yeah. Well, no, the relation between them is that ice crystals require insoluble aerosols, right? So the number or the concentration of ice nuclei is going to increase as the concentration of insoluble aerosols increases, right? Because ice nuclei need insoluble aerosols. Any other questions? Yeah. What say that again? Yeah, it needs to, yeah, so the cumulonimbus cloud has to be generating rain, otherwise it would just be a cumulus congestus, right? Because it's by like naming or nomenclature. Okay, so yeah.
So, like, I'm not really sure
Yeah, so if the wind bar is like this, the wind bar was like this, it means that, again, like I said, I imagine I'm like, you know, in like King Arthur or something, and I'm firing an arrow, and it's stuck into a board here, the wind direction is pointing that way, so this is southwesterly, right?
So it's the way that goes into the.
Yeah, exactly. So it's pointing in the direction in which the wind is going. So
Not
that's
the entrance, right? Okay.
yeah. So if I drew a circle, if I drew the holograph,
Yeah. Okay.
right, it would be pointing that way, right? So from southwest to northeast, this is the direction of the wind. This
So
way.
the wind's going.
Does that make sense?
Yeah.
So, yeah, so if there's wind bars on a map, then, like, this would probably be,
Okay.
there would be a low pressure there, and the isobars going around like this, the wind would be like that above the surface, right?
Yeah.
Other questions?
Can you explain like surface pressures underneath upper level troughs and ridges?
Yeah, so that's kind of what I was talking about with the 300 millibar surface. So if I have, if this is height, Z is denote height, and then this is distance on this axis, let's say that's X, right? And let's say the surface low pressure here, right? We can't really draw the isobars, but it's a cyclone at the surface. So if we looked at a map, horizontal map of the surface, you'd see a low pressure here, and there'll be isobars around it, and then this would be the center of low pressure. The wind would be circulating around that, maybe converging in the middle. So there'd be something like this going on, because of course the friction is causing convergence near the surface. At upper levels, if I have a trough like this is low pressure up here, right? Again, we look at this on horizontal surfaces, right? So we would have to look at this trough like this. And so what we would do, if we look at this height, right, or let's say we look at this pressure surface, whatever. If we look down from above on that surface, we're going to see relatively low heights of the pressure surface, right? Because let's say this is the 300 hectopascal surface. There's two ways to look at maps in the atmosphere, okay? The one way to look at maps in the atmosphere is looking on the pressure surface, okay? So if I followed the 300 millibar surface like we were talking about a minute ago, the height over here would maybe be, you know, something like 10 kilometers. But here, I mean, I've exaggerated this picture to draw it here, but it would maybe like 9.2 kilometers or something like that, which means that the height of the 300 hectopascal surface is dipped by 800 meters. Why would the why would the trough be why has the 300 hectopascal surface dipped? What is true about the column of air here versus over here? More dense. Good. It's more dense here, which means that it's colder. Right? So think about this picture for a second. Right? What do we know we get behind departing low pressure systems? We've seen it lots of times recently, right? We have the cold front coming through. Right? I'm obviously drawing up a picture, whatever's down here. But there's a cold column of air behind the low pressure system, right? And out in front of it, there's a warm front. Right? Warm front, and there's a cold front. The cold column is spilling out southwards. That's what the disturbance does. It actually breaks up the balance between the pressure gradient owing to the temperature gradient that exists and the inertia, the Coriolis force that's keeping it propped up, and it allows it to spill southwards, right? And that's what comes in behind the cold front. So over the low pressure, which is actually, remember the word, downstream, right? Because the winds are going this way. I drew another. The flow is moving from west to east, in the majority of cases in the latitudes. And so what is happening is, and this is kind of a little bit more of an advanced topic, but above this surface low, the advection of this spin over this area, and remember advection just means movement in the flow from one place to another, the advection of this spin over the top of this surface cyclone, remember that we are downstream of an upper level trough and upstream of an upper level ridge. I should keep drawing that up there, like that. So the ridge is over here somewhere, the trough is right here, right? Downstream of the upper level trough and upstream of the upper level ridge, we have divergence. So air is pulling towards the low here and is being pushed away here. The reason that happens is literally because I'm taking air. Remember we were talking about the thunderstorms earlier that rotate, right? What did I say about thunderstorms that rotate underneath them relative to ones that don't? They have lower pressure, right? Because if they're rotating, there has to be some force balance between pressure gradient and centrifugal force. The same is true in the atmosphere. There's some force balance between this low pressure and some inertia. So that is lowering the pressure there. That is moving above. That is moving above the region of low pressure at the surface, causing flow to diverge, right? So we have upper level divergence downstream of this upper level trough, which creates lift over the surface cyclone, right? So now we have flow converging into the surface cyclone and rising into the atmosphere downstream of the upper level trough, and then there's upper level divergence there. So this is the relationship between an upper level trough, an upper level wave in the atmosphere, and then a surface cyclone at the ground, right? Does that make sense? So what happens if this guy becomes vertically stacked with this guy? Now there's no source of deepening, right? So if the wave becomes vertically stacked, then the cyclone is not going to deepen anymore because there's no upper level divergence out ahead of the wave, right? And then if you're upstream of an upper level ridge, the opposite is true, right? I'm not going to go into this in too much detail, but just to say that the ridge here, if I am downstream of the upper level ridge, I actually create convergence. And that leads to subsidence and high pressure with air spiraling out this way. Away from it. So, if you look at that convoluted pattern, bloody right a bit. You see the upper level trough is upstream of the surface low because it provides divergence at upper parts of the atmosphere, lowering the surface pressure. The upper level ridge has associated upper level convergence with it up downstream of the upper level ridge, which increases the pressure through convergence and subsidence, causing high pressure at the surface. So that's the relationship between upper level troughs, surface lows, upper level ridges, and surface high pressure systems. Right? Does that make sense? Yeah. Any other questions? Anything else, yeah? Yeah, the answers to this test, even though we went through it today, the answers to this test, oh, you mean this other one? Yeah. I will try. What we'll do first is post the answers to the one we went through. I'll post the extra questions. Right, so I'll post another test, so you have that. I will then try to discuss that other test on Canvas. I'll jump in where necessary, and Srinath and Kate will jump in where necessary. But you guys, between the 350 of you, probably know the answer, right? So have a discussion on there. It will promote you guys thinking about the concepts and learning it better. And then I'll jump in if need be and answer the question, just like I did with the microphysics homework this week. So that's going to be your best bet. I'll try. I've got like 2 talks, a poster, and a conference to get prepared for, so I'm kind of stressed out. But yeah, I'll do my best and we'll figure something out, but we'll definitely get other questions, which again, study those questions because the likelihood is at least a few of them are probably going to show up, right? Does that make sense? So, good idea to go over them. We'll get as many up there as we can, another 50 or so, so you can probably have a 1 in 4. 1 question in 4 might be able to.
When will the video be posted?
Monday, so we'll get that up on Monday. Anything last? Yep.
Does friction affect Coriolis effect?
So friction affects the wind speed. The wind speed is the wind. The faster the wind, the greater the Coriolis effect. Because imagine you're moving faster relative to the planet, the Coriolis effect is greater, right? So the friction affects the wind speed determines the magnitude of the Coriolis effect. Everyone feeling a bit better now? Okay, thank you. Alright, that was the goal of this.
I didn't even realize that surface high, is that spinning anti-cyclonic?
Yeah, so this is anti-cyclonic. That makes sense?
Yeah.
Clockwise in the northern hemisphere, anti-cyclonic. Cyclonic is anti-clockwise.
Why is it flipped?
In the southern hemisphere, because the Coriolis effect is the other way. It deflects water to the left. Right? Does that make sense? Because imagine you're at the equator traveling south, right? The Earth is spinning, like imagine I'm an equator going south, the Earth is spinning this way. So as I go, think about this.
Actually, yeah. You go left as the
Right.
Earth spins.
Yeah.
So if I throw a baseball from here through the air, the Earth spins this way. So instead of landing where I thought I was going to land, it was kind of deflected to the left, right? Whereas if I throw it from the North Pole toward the south, it's not going to land where I deflected it. It was deflected to the right. Does that make sense?
Yeah.
Okay. So because of the spin of the Earth relative to where you are latitudinally, the effect of the Coriolis force is deflect flow to the left in the northern hemisphere. Southern hemisphere and the way in the northern hemisphere.
Yeah. Yeah.
So that's why the spin happens. Not fact. Everyone asked me the other day, I was doing a discussion section, and I was showing a global temperature change over the years, and the Arctic had warmed a lot more. And I remember asking the question, why is the Arctic warmed a lot more? And at least two people in different discussions told me that it was because hot air rises. And I was like, oh boy. Oh, we got a long way to go.
Oh, dear. Thank you.
All right, thanks guys.